Welcome to the pod, Cultivating Innovation, one batch at a time. This is biomanufacturing and fermentation technology.
Welcome back to the deep dive. Today we're tackling a topic that's, well, it's quietly rewriting the rules of manufacturing chemistry. We're talking about cell-free biocatalysis.
And it is a massive transition. I mean, for decades, these systems were, largely an academic novelty.
Just something you'd see in a lab.
Exactly. But now they've moved way past that niche concept phase. Cell-free biocatalysis is now a deliberately engineered industrial platform. It's ready for prime time.
And the reason this is so critical, the real core benefit that makes it worth, abandoning the whole living cell is control.
Absolutely, control.
When you strip away that cellular envelope, you get direct, fine-tuned control over the three big things that historically blow up a commercial scale-up.
Yeah.
The purity of your product, the efficiency of the reaction, and crucially, mass transport.
And that control translates directly into cost savings and reduced risk at high volume. If you can't manage those three things, transport, purity, and reaction control, your yield just collapses.
And your purification bill goes through the roof.
Astronomical, yes.
So here's our mission for you today. We need to understand the practical drivers, the industrial and financial reasons making cell-free systems not just possible, but economically viable right now. We'll dig into the criteria experts use to define an industrially fit enzyme, and then unpack the engineering strategies that turn these, fragile biological tools into stable, reusable manufacturing components.
Oh, it's good.
Okay, let's unpack this by starting with the most compelling driver, selectivity. When you're looking at high-value products, especially in pharma, why is an enzyme the go-to tool over a traditional chemical reagent?
It really all comes down to efficiency, stereo control, and just eliminating unnecessary steps. In traditional synthesis, if you want to create a specific chiral molecule one mirror image, you often have to use these lengthy multi-step protecting group strategies.
Right, just to guide the reaction where you want it to go.
Precisely. And you use stoichiometric reagents that get used up, which creates a ton of waste. Enzymes just cut right through all that complexity.
So they achieve the same result, but in one step with minimal junk left over. That's route shortening at its best.
It is. Enzymes mediate these high selectivity transformations in a single step. We see this perfectly with two sort of archetypal industrial reactions.
Okay.
One involves ketoreductases, or KREDs. They perform asymmetric reduction to make chiral alcohols. The other is the acetyltransaminase, or POTA, which is used for amination to create chirolamines.
And in both cases?
In both, the enzyme's innate stereo control just displaces all those complex multi-step protection strategies. It simplifies everything downstream and dramatically lowers the purification burden.
That selectivity advantage is clear. But why take the big step of getting rid of the whole cell? I mean, whole cells are generally cheaper to grow. What's the price you pay at high volume for keeping that cellular shell? The sources talk about a scale-up failure map.
Yeah, it comes down to basic biological constraints that become financial bottlenecks at scale. First, many valuable substrates or products, especially hydrophobic ones, are just plain toxic to the cell.
They poison their own factory.
They do. They compromise cell viability, they damage the membrane, they can interrupt ATP production. The whole thing just grinds to a halt.
So the cell essentially kills itself trying to make the product.
Exactly. And second, you run into transport limitations. It doesn't matter how fast your enzyme is working inside the cell. The overall rate is capped by how fast the substrate can physically get across the cell wall.
So the cell wall itself becomes the bottleneck.
The kinetic bottleneck, yes. And finally, you mentioned it before, purification.
Right, the complexity.
Precisely. Whole cell fermentation generates tons of biomass and other cellular machinery. All that biomass leads to background impurities, proteins, lipids, you name it, that make purification a nightmare, especially for high-purity applications like pharma.
The cell-free solution, then, just sidesteps all of that by freeing the enzyme.
That's the core freedom. Cell-free systems let process designers operate in non-standard media, like aqueous organic mixtures or biphasic reactors. This dramatically increases substrate solubility and volumetric productivity.
To levels that an intact cell could never handle.
Never. We're targeting substrate loadings that are economically essential, not just biologically permissible.
Speaking of which, there's that harsh reality of high loading or it won't scale. You're trying to get product concentrations in the pentagrams per liter. How do you do that in a system that still has chemical equilibrium limits?
Well, the key industrially recognized lever is something called in situ product removal, or ISPR.
ISPR.
You have to actively remove the product as it's being formed. This is especially true for equilibrium-limited reactions like transaminations. You do it to shift the reaction equilibrium forward and suppress product inhibition.
So when you say ISPR, using an ion exchange resin for a chirolamine, for instance, what's actually happening on a mechanical level? Is the product bonding to the resin?
It's an electrostatic capture, really. For chirolamines, the amine product is positively charged at the working pH, so it gets captured by the negatively charged resin.
Ah.
And this is so crucial because removing the product prevents it from interfering with the enzyme or shifting the equilibrium backward. This technique has enabled transaminase concepts to operate at around, say, 50 grams per liter of substrate.
Wow, 50.
That's the kind of tangible metric that makes cell-free a real industrial tool.
Okay, so to sustain those high loadings, you need enzymes that are truly industrially fit. And this means a totally different approach to discovery than, old school academic research.
A completely different mindset.
So we're moving away from just looking for the fastest enzyme in a petri dish to something more holistic. What does this new discovery funnel look like?
The foundation is still screening natural biodiversity, but all the steps after that are engineered. The screening panels themselves are designed around known industrial constraints.
For instance?
For an OTA, the screen isn't just measuring speed, it's prioritizing its scope, its tolerance to cheap donor and acceptor molecules, and most critically, its inherent stability.
So the stability of the enzyme under, say, high-pressure, solvent-rich conditions is what makes or breaks it as a candidate, even if another enzyme is technically faster in a lab.
Absolutely. Process-relevant challenges, thermal stress, solvent exposure, resistance to inhibition, they often dictate the achievable performance at scale. They dominate over pure catalytic speed. That's what we mean by industrial fitness. It's activity and selectivity plus stability under real operational conditions.
That makes perfect sense. And how do you measure that stability in an industrially relevant way? Because operational lifetime has huge financial implications.
It has to support long industrial campaigns. We're not talking about half-life in a test tube. We're talking about its half-life when it's running continuously under flow for days or weeks.
Okay.
For instance, some continuous packed bed studies using immobilized 2-ETA systems have shown multi-day operation. I think a common benchmark is around 96 hours with no detectable loss of activity.
That 96-hour number feels very specific. Is that like a minimum industry standard for a successful continuous run?
It's the necessary proof point. A 4-day continuous run proves that the enzyme can withstand the operational stress of a continuous setup. It can handle the temperature, the solvent, the flow without just falling apart. If you can't hit that, you're pretty much stuck with batch processing and all its inefficiencies.
And the other big factor for fitness is resistance to inhibition, which we touched on.
Inhibition sensitivity is the hard ceiling. It really dictates how high you can push your substrate loading and therefore your productivity. An enzyme that's super sensitive to substrate or product inhibition will fail economically, even if it's cheap and fast, because the economics demand high concentrations.
Right. So moving from discovery to a large-scale plant requires some serious reaction engineering.
Oh, definitely. In cell-free practice, substrate and product inhibition aren't just, footnotes or edge cases. They are common mechanical features you have to explicitly engineer around.
Okay, let's break that down. Substrate inhibition, how did that work? And how would a process engineer spot it in their data?
So substrate inhibition happens when, at very high concentrations, the substrate molecule binds to the enzyme in a non-productive way. Maybe it binds at a secondary site and blocks the active site.
And in the data?
In design of experiment, or DOE data, this shows up really clearly. The reaction rate goes up as you add substrate, it hits a maximum, and then you see a distinct decline in the rate at even higher concentrations. It looks like a bell curve.
And product inhibition, I'm guessing that's more of a time-dependent thing.
Precisely. Product accumulation can shift the equilibrium backward, like we said, or the product itself can physically block or even deactivate the enzyme. In the DOE data, this looks like a time-dependent rate decay that's strongly correlated with conversion. The longer it runs, the more product you make, the slower the reaction gets.
So what are the pragmatic, scalable fixes for these kinetic issues, beyond that ISPR we talked about?
Well, ISPR is still the key for product inhibition, especially with those ion exchange resins for transaminations. But another critical fix is continuous flow processing.
No chemistry.
Right. Flow processing lets you control the residence time very precisely, so you can decouple the conversion from that inhibitory accumulation. It lets you run at a steady state.
That's a sophisticated chemical engineering tool being applied directly to biology. Now, what about the reaction medium itself? You said it's an active engineering lever, not just a solvent.
Media engineering is fundamental. For systems running in aqueous organic solvents to boost solubility, water activity has been identified as a key stabilizing variable.
Wait, water activity. So you're talking about regulating the actual humidity or the amount of free water inside the reactor. That sounds incredibly precise.
It is. The enzyme structure depends on a certain layer of hydration to maintain its catalytic flexibility. Controlling water activity prevents it from getting too dehydrated or, conversely, too solvated, which can trigger deactivation during intense operation. It just keeps the enzyme in its happy native state.
And what about simple things like pH and ionic strength?
Oh, they're critical, actionable levers. pH and ionic strength shift the speciation of the substrate and the product, basically changing their charge. They also affect the ionization of key residues within the enzyme itself. Changing the buffer formulation can change both the reaction rates and the enzyme's overall stability. It's a core part of the design.
Since we're on continuous flow and reuse, we have to talk about immobilization. Why is sticking the enzyme onto a solid carrier the key interface for continuous manufacturing?
Because it transforms a fragile, soluble catalyst into a durable, separable unit operation. Immobilization is crucial. It delivers reusability, enhanced stability, easier separation from the product, and most importantly, it makes it ready for continuous packed bed formats. Without immobilization, you just can't get those long campaign lengths you need to be economical.
When designers are picking that carrier, the material the enzyme is stuck to, what trade-offs are they juggling?
It's a negotiation between engineering principles. The first challenge is mass transfer limits. If the enzyme is stuck deep inside the pores of the carrier, you can get pore diffusion limitations that suppress the enzyme's effective rate.
So the enzyme is fast, but the substrate can't get to it quick enough.
Exactly. So to solve that, you might think, let's use smaller particles for better mass transfer.
But there's a trade-off.
A big one. Smaller particles drastically increase the pressure drop in a packed bed reactor. That pressure drop really tightens your allowable flow rate and viscosity windows. So you're constantly balancing particle size against the system's hydraulics.
And then there's the risk of the enzyme just falling off.
Leaching. It's a critical industrial failure mode. The enzyme gradually comes off the carrier, contaminates the product, and forces a shutdown. That's why covalent immobilization, chemically linking the enzyme to the carrier, is so common. You might take a small hit on initial activity, but process designers will almost always prioritize reliability and zero leaching over that marginal loss.
This brings us back to that core theme. Once the cell is gone, everything has to be designed.
Yeah.
Can you use cofactor-dependent reactions as an example of that kind of explicit systems engineering?
Certainly. Many industrial reactions, like those catalyzed by KRADs, need a cofactor like NADH or NADPH, which gets consumed.
Yeah.
Since the cell is gone, we have to regenerate that cofactor to keep things running. In continuous systems, we often use co-immobilization.
Co-immobilization.
Yeah. The main catalytic enzyme is stabilized and paired with a separate cofactor regeneration partner, often an inexpensive dehydrogenase, on the very same carrier particle. This whole engineered system sustains conversion under flow. It's a perfect illustration that every single component, from the main catalyst to the energy recycling system, has to be engineered for the process to work.
Okay, so let's look at how these principles, selectivity, stability, control, are prioritized differently across some major industrial sectors, because the end product changes the mandate, right?
It absolutely does.
Let's start with biopharma. They're often the leaders in adopting this kind of high-precision synthesis.
For biopharma, the focus is, without a doubt, on the impurity profile and consistency. The key applications are things like chiral building blocks and late-stage functionalization of drug molecules. Both KREDs for chiral alcohols and POTAs for chiral amines are considered mature, industrial-age applications here. They're valued not just for speed, but for their incredible stereochemical fidelity.
And that fidelity means less cleanup.
Exactly. It minimizes regulatory risk and drastically reduces the burden on downstream purification, which is incredibly expensive.
Okay, next up, food, agriculture, and animal feed. The constraints here seem much more rugged.
They shift dramatically to thermal and operational stability. Enzymes like amylases and proteases are used as processing aids to modify raw materials, but their use often happens during high-temperature processing.
So the heat is the killer.
The thermal exposure during manufacturing is a major activity loss mechanism. So for this sector, stability at high temperatures is the absolute frontline requirement. It often takes precedence over pure maximal activity.
And finally, biochemicals, where the focus is on converting renewable feedstocks. What's the driver there?
For them, it's primarily about route shortening and maximizing the overall yield from that feedstock. They use these cell-free systems to convert renewables into specialty intermediates. The big advantage is viewing these in vitro systems as modular enzyme sets.
Like Lego bricks for chemists.
Kind of, yeah. This modularity lets designers assemble a series of selective transformations into much shorter, higher-yield routes, and they can explicitly avoid any unwanted side pathways that might exist in a living metabolizing cell.
It's fascinating. The same foundational technology, bio-catalysis, is solving three totally different commercial problems. High purity for medicine, high thermal tolerance for food, and maximum yield for specialty chemicals.
That's the perfect takeaway. The enzyme's inherent selectivity enables these simpler, cleaner routes. But you only capture that advantage economically when you pair it with a process-fit enzyme, an engineered reaction environment that avoids inhibition, and a stable, immobilized format that's ready for long industrial campaigns.
So if we synthesize all of this, the true value of cell-free biocatalysis really comes from the cumulative alignment of three things: selectivity, robustness, and absolute process controllability.
That alignment is where the commercial benefit is. The enzyme's biochemical precision only delivers its full financial value when it's paired with an engineered environment that can handle high substrate loadings, actively suppress inhibition with things like ISPR, and enable a completely predictable impurity profile.
So cell-free systems aren't just an alternative to fermentation. They're really a complementary manufacturing paradigm that's optimized for predictability. It's a blend of biochemical precision with chemical engineering discipline.
And that's really the challenge and the opportunity for anyone learning this space. It's understanding that once you remove that cell boundary, you inherit the responsibility for everything the cell used to manage implicitly. Cofactor balance, heat exchange, mass transfer, catalyst lifetime, it all has to be explicitly designed and controlled.
And the next frontier.
The ultimate challenge might not be engineering a single enzyme system, but integrating 10 or 15 of these cell-free engineered modules into one streamlined, continuous flow chemical plant. That integration, that is the next frontier in process complexity.
How do we solve the valley of death in biomanufacturing? It starts with better data and more robust fermentation technology. Join us on Biomanufacturing and Fermentation Technology by Prasad Ornala for our upcoming series featuring lead researchers and process engineers. We're discussing everything from bioreactor design to downstream processing, DSP efficiency. Follow us now to join the conversation on the technical frontiers of biology.